Would you like your second hint now?
Yeah, okay.
So, hint number 2. Do you remember when we talked about n cubed and how you made me think of a new solution idea?
Yeah, vaguely.
Where we end up using a segment tree?
Mm-hmm.
We can do something similar here. So, let's imagine our sort of iteration on the midpoint, the mid row or column. Let's call it the divider.
Mm-hmm.
We're double iterating through locations on the divider. If we fix, let's say, for argument's sake, the top location, I'm just going to imagine without loss of generality that our divider is a column, a column segment. So we'll fix the top, and now we're just going to imagine iterating through bottoms.
Okay.
What's going to happen is at each point, there's actually sort of second, there's a left side and a right side, right? Mm-hmm. I'm just going to define the logic as though we're looking to the left.
Hang on, I got it. I think I got it. Maybe. Hang on. Give me a sec. This is kind of reminiscent of the square version.
Do you agree when we've got a top and a bottom, and we're definitely trying to just find the left side of the rectangle we can make that crosses the divider at that top and bottom? Do you agree that there is a limit to how far left we can go based on just how many black pixels there are at the going left at the bottom and going left at the top? So we get this range, like we're only looking in this range.
Yeah, for sure.
And in that range, all we care about is finding a column segment that spans from one side to the other that is all black.
Oh, you mean like the lid, right?
Yeah, the left lid.
Yeah. Yes.
So this is a problem we already know how to solve because we solved it before with the n cubed log n solution where we just put them in a segment tree. No, because you need to find the leftmost one.
Oh yeah, the leftmost one. Yeah, sure.
Yeah. That exists. So it's kind of like you need to put them in like a set or something.
Yep, got it.
Yeah, the leftmost one that's definitely falls within our range. So you can sort of binary search for the pointer where the left end point of your range would search, and then find the first thing after that.
Yeah.
So we can put them in a set or a segment tree or whatever, any kind of range searching data structure here.
Mm-hmm. So
this gives us n squared log n to do our processing, which means our whole solution's n squared log n. Now the real difficult part is getting rid of that log factor.
Oh, that's the difficult part? All right, fair enough.
So maybe I'll just like run through it for completeness.
Well, let me just give my thought then. In order to get rid of the log factor, you need to reuse the computation somehow between like the iterations, right? And then, but how do you do that, right? Well, you probably need to make like some you need to like make some like relation somewhere, like maybe it's like the columns as like they get longer, or maybe it's like to do with like the left to right range as you go down and how it changes.
I'll give you the key insight without actually telling you how to do it.
Okay.
Suppose I fix the top row and I'm iterating over bottom row on our divider. This range that we're looking up is monotonically decreasing. Like how far out we can go monotonically decreases, sort of. That's not the right way of describing it because that's actually not true.
Well, you're talking about the fact that the you can always use a longer column as like a longer lid as a shorter lid, right?
My point is that columns monotonically switch from being possible to not possible.
Yes, exactly.
So columns only become inactive.
Yeah, that's right. Yeah, I agree with that because you can always use a longer column as a shorter column, a longer lid as a shorter lid. Right, you don't need to use all of the lid. Use a portion of the lid. Yeah, so that's true. That's true. That's true. Pretty true. So your range is always your left-right range is always getting smaller. The possible range you could.
Well, I mean the range you can use as forced by the
lids.
The top and bottom of where you are in the divisor, like may go around randomly, but the left lids you can use the set gets smaller and smaller as
which
you go
means
along.
you can define like ordering on the lids, like of like if you're at like this like left point, then like you have to be like you got to use like this lid or like any lid after it, right? Like some
Yeah, so they are all only active for like a prefix, right?
yeah.
Oh, maybe I can't completely get rid of the union find like data structure.
Well, I mean, you can do like event simulate. Well, like event simulate like when like the lids come in and right. Just be like, I'm gonna start with this lid, and then like if it's too far like to the right, I'm just gonna like come in, whatever.
But you still need to be able to find quickly find the first lid to your right that is still active. That's still the tricky part. The tricky part is solving that embedded in the log time. Of course, this is where union find comes into it, right? Because you just look for the component that it's in. Sorry, that's not a very clear description. You can keep sort of components where every node is a column and two columns share an edge. Like, if they both don't exist. And so, yeah, it is confusing. I agree. Imagine every column is a node, right?
Okay.
Initially, everything starts off active, like it's a valid lid. Mm-hmm. So we'll say the node is completely disjoint. It's its own thing.
By columns, do you mean the lids or the actual columns of the grid?
The lids.
The lids. So the contiguous sequences of black squares.
Yeah. When a lid becomes inactive, we will union it with the thing to the right, because what we're saying is I can no longer be a lid. Something to my right can be.
Right. So the yeah, this is exactly the same as the square version, right? Like
it is, yeah.
It's like this is probably like generalizable as a technique, right?
Yes.
So like
it actually might be an interesting paper.
Yeah, like, that's interesting.
Generalizing this idea and seeing what you can solve with it.
Yeah, so that what the idea is that well, are you like, can you just find like any column and then find its like representative and be like, this is my thing? Or do you have to like us have like a specific column, like I was at this one, but now it might be inactive, so like find like the active one. Like as you go down, like how do you decide which inactive column potentially active to query the representative of?
Oh, so you have like a left extreme as governed by the 2 points on the divider that you've picked. You just look up that lid and just say, give me the first lid to the right that is active. So you just look up its component in the disjoint set, and it'll tell you, right? Because for every component you store this information.
I see. So all right, so yeah, there's a bunch of stuff that are worth going over, I think. So the lids we have, the assumption we have, or like the invariant we have, is that all of these lids intersect the horizontal like edge that we've selected as the top, right? And then what that it's still possible for there to be multiple lids per column though, right? You can probably deal with it somehow.
No, it's not possible because it has to span. We've fixed a top.
Yeah.
Like, remember, the whole setup is that
you just ignore it.
This monotonicity is only as we sweep over one of the indexes in our two indexes.
Yeah. So
on the divider.
Right. But I guess the assumption is that the lid has to intersect with the left edge of the top thing we selected, right? So there has to be 0 or 1 lids per column, or like a pixel in the top edge, right?
Right.
Yeah. So that means that when we're looking at a particular bottom thing on the midpoint, we can go
The divider.
on the divider. Yeah. On the divider. We can go to the its leftmost black pixel, but also we got to min that with like the length of the top edge as well. And then you look up the lid at that column, and then you get the representative of that column, which is going to be the leftmost active lid that is to the right of that one.
Yeah. Which is always the one we want.
And since it's active, it's guaranteed to span between that top and that bottom.
Yeah.
And then all you have to do is at like the end of each like bottom thing, you just like deactivate and like merge things to the right.
Yep. You just do your union. All you need is union and find.
Union find is all you need.
Yeah, that's right. What a paper.
Yeah, that's not the easiest question I've heard.
Yeah. And the trick here is you can get rid of inverse Ackermann because this is not a normal graph. It's a special kind of graph. It's a line graph. So you can do tricks to get rid of the inverse Ackermann. Not that you actually would in practice, because who cares about the frankly constant factor in practice that is union find, and also a very small constant factor at that.
I think Ackermann probably cares.
Nah. He doesn't care, but inverse Ackermann does because he's inverted.
All right. Yeah, true. That's pretty true.
So this is my my rectangular outline question.
Thanks. I hate it.
You're welcome.
No, it's pretty good. It's to be honest, it's like the square one but harder.
Yeah, I agree. There's a lot of layers to this one. I feel like this would be a good
onion
problem. Yeah, so this is a problem where there is a layer for almost every level in informatics. Like the end of the five, I think first year who's learned how to use their programming language well can probably noodle out, right? The end of the four is a pretty good level to expect someone in a realistic interview.
Yep.
And then n cubed is reasonably advanced algorithm nerd or informatics contest participant. And then n squared is like, grandmaster level.
Yeah, n squared. Yeah, that's pretty hard.
Yeah, it's much like an ogre, this question.
Much like a cake.
Got a nice frosting.
Nice frosting with a disgusting core.